So first and foremost, right, I didn't yet add those people if you are here, 2 more that joined my email list. So if you are not on my email list, make sure that you will be. Send me a message. So I add you up and I can message you. For example, once the exam comes about, it will be mentioned several times in class and several times in an email, I presume. Good. You will not miss it. The exam will take place after we cover trigonometry. After we will have covered trigonometry, then you can have the exam. So if you have a question, when is the exam? After we have covered trigonometry. So there is still some time to go. That will be when I see that you cover trigonometry, right? It depends on you guys. It can be tomorrow if you already covered trigonometry, or it can be in a month if that's how long it takes, right? That's why I cannot say how long, right? Do you understand the lectures? I try to keep you afloat. Yes, another month. I would have, you see, guys, so a few things to say about it will be before, during, and after Pesach, Nicole, right? Mathematics is all through, kind of like the name of God in Hebrew. So guys, if you could, please do me this very big favor and turn your camera on if you have it. As you know, when I begin seeing fewer and fewer people, I feel maybe I feel insecure. Maybe I'm not entertaining you enough. Thank you, Jomal. Thank you, John. Thank you, Toho or Tojo. And so guys, so far from the morning class, some people come a little bit less. I hope in this class you don't have that temptation. And I also posted the textbook called Calculus for Dummies, right? Some people found it useful, and I'm hoping you might also. If you find some of my explanations a bit too steep, you can try reading that book. Maybe that would help you catch up. But guys, by God, by Almighty God, please study. Not just in my class, please study after class and before class. When I learned calculus, I spent, and I taught myself calculus over a summer, I spent 4 hours a day doing it. And I was very focused. 4 hours every day. And that's me, you understand? I was never too bad at it. So that means that if you are limping a little bit, then you need to do even more. You should also be registered for the website My Open Math. So be sure, guys, not to delay with that. Register for My Open Math, right? That you will be able to take the final. Nice to see you, Alexandra. Thanks for coming. Thank you, guys, all of you that. How do you register, Elazar? It seems that you haven't looked at my syllabus. Look at the syllabus. The instructions to register are there. Wonderful. Well, let's begin with the lesson. Yes, guys? And also, guys, we'll see today. I will do my best to carry some part of office hours. I mean, I have a few things to do in the evening, right? So I might not stay for the full time. All right. So here is a review of what we've covered last time. I'll try to go quickly through it. The derivative of an exponential function, we can use this definition of the derivative. And what do we observe? We observe that we end up, Dauda, about email, I said you should be on my mailing list, right? And the instructions to do that, or you can see in the syllabus, you can see my email. Just mention you're a calculus student in the evening section, and full first and last name. What chapters should, guys, do you open my notes? What you should be focused on is my notes, and you can see the exams. You can see that the sequence of notes that I produce correspond to the lectures in your book. Okay, so it's chapter 2, chapter 3 right now. Right, such questions, I mean, do you open the book at all? The derivative of a function e to the x is a to the x plus h minus a to the x over h. Look at it, I factor it out. And what do I observe? Simply symbolically, I see that the derivative of a to the x is the function multiplied by the derivative at 0. In other words, the derivative of a to the x is essentially a to the x multiplied by some number. What is that number? Because we have technology, and some of you use technology way too much, we can ask the calculator. We can do this calculation and we can estimate that the derivative of 2 to the x at 0 is roughly 0.69. And that means that if I take derivative of 2 to the x, it's the same as to multiply 2 to the x by 0.69, more or less. You're with me, guys? If I take the derivative of 3 to the x, the derivative is more or less multiplication by 1.099. Now, if I take many derivatives, and many derivatives you have to take, then you would have to multiply many times by, let's say, 0.69. And this multiplication is not very pleasant. So then you think, what's the most pleasant multiplication that I can have? The derivative of some exponential function is the exponential function times some number. I cannot hope for that number to be 0 because the derivative of an exponential cannot be 0 as this is not a constant function, right? Derivative 0 means everywhere I look on the graph, the slope is 0. We have a lot of horizontal line segments building up the curve. So the derivative of an exponential function cannot be 0. Therefore, the constant cannot be 0. Is that clear? Yes. So the next best number is 1. You agree? Multiplying by 1 isn't very challenging. You just, it's essentially don't do anything to the original expression. So we, by playing with the calculator, which is again, guys, my God, I want to close my eyes. You see, technology is getting better and better and better, right? You can make a computer is almost sentient. Sometimes, you know, you give it a translation of a poem and it gives you the meaning of it. It's scary what a computer can do. You show a photograph of a cat to a computer and it recognizes it, right? So the computer gets smarter, but the people using it get dumber. And that really is, to me personally, is sad. So what we're trying, define dumb. Dumb as in, you understand, you have a helmet, right? When you ride a bicycle. Imagine that the helmet is now, the helmet is supposed to protect your head. But imagine that we reverse it and now the head protects the helmet. The head is a sort of sponge used to absorb the impact for the helmet. That's what I mean by dumb, right? And that's what I do not want you to be. I want you to understand, guys. So it's a bit also, you know, for myself too, you understand there is going to be very soon a level where a human intelligence is going to be totally obsolete, I think, right? But hopefully not today. And hopefully you are not very excited about this, that moment. So we are assuming that there is a number e between 2 and 3. And that hypothetical number will have the limit as h goes to 0, e to the h minus 1 over h equal to 1. Now, you see, when I constructed this number and realized it's between 2 and 3, I was already cheating because I used a computer. And when I use the computer, I mean, if it's just doing tedious works, that's what's wonderful. But if you understand what the computer is doing, do you know how to take roots of numbers? Can you take root of 2 by yourself if you had to? Do you at least, can you describe a procedure that will compute root of 2? And what about the 1000th root of 2? If you do not know a procedure, then essentially, well, you're exporting this question. You're a believer. You're sort of accepting that the calculator gives you the right solution. And calculators were not around when those ideas were invented. So what we are going to do is actually, instead, guys, and let me try to explain this very confusing moment. Right? I think you're not accustomed to think this way. So exponential functions, guys, yeah? Do you understand what it means to exponentiate? Right? So you do know what it is to take a number like a number like 2 to the power of x, right? What is it that we're doing? Think about it very carefully. Well, what is 2 to the power of 1? That's just 2. That's easy, right? 2 squared, that's easy. That's just multiplication. We kind of know what it is. Yes? So 2 to the power of any integer n, it's just 2 times 2 times 2 times 2, where this is 1, 2, 3, n times. It's just bookkeeping of multiplication. So far, exponentials are very clear. If you think a little bit, then it's clear that 2 to the power of n multiplied by 2 to the power of m, where n and m are integers, that will give you 2 to the power of n plus m. Yes? That's easy to figure out. It's just still bookkeeping. But guys, as soon as we get to fractional power, so for example, I ask you what's 2 to the power of 1/2. That's root 2 symbolically. Now, what is root 2? Now you are stumped. You don't know how to calculate it, yes? But maybe you can say, well, that's just still understandable. That's a solution to the equation x squared equal to 2. And what is 2 to the power of 1/3? That's a solution to x cubed equal to 2, presuming that I can solve it, right? I mean, in your school, you were just saying the answer is cube root of 2, but you did not understand what the answer means. You just gave a name to that x. You understand? Just because you wrote 2 to the power of 1/3 does not make it supposedly more understandable. Do you agree? Because when you press 2 to the 1/3 in your calculator, the numbers are spat at you. By the way, don't worry. I will teach you a little bit about calculating roots. Okay, I will teach you how you might calculate roots. If you actually thought about it, you could have figured it on your own, I'm sure, if you think about it long enough. Good. Now, there is even a war situation, guys. Now, what does it mean to take 2 to the power of root 2? You can put it in your calculator, and your calculator will spit some numbers. But what does it mean, guys? If you ever bother thinking about it, what am I multiplying 2 by itself root 2 times? What does it even mean? What does 2 to the power of pi, what does those things mean? So in general, 2 to the x is very mysterious. You understand? I used exponential laws, I did whatever I did, but that's very mysterious. I haven't developed those ideas deeply. I haven't thought about it. Are you with me? You understand? I mean, I'm saying something that maybe completely screws your circuits, but are you with me? I haven't yet completely fried your brain, yes? You understand what I'm saying? Yes, Sarah, yes, Sophia, yes. Stay with me, guys, right? I'm saying something confusing, but only because the subject itself is very confusing. So then I make the following adjustment, guys. I say, okay, I have no idea what is an exponential function, but I have some sense of what is a derivative. Derivative is just slope. You have just a lot of lines. Derivative is a slope. It's a very, very easy idea, right? Nothing to think about. Here is a curve. Now, I imagine that this curve is built of many small line segments, right? That's what I do with the limit. I'm just describing an obsessive approximation. But really, I think of this curve built of line segments. And the derivative is just mentioning what's the slope of any given line segment. Right? I just imagine the line segments getting smaller and smaller and smaller, and the limit tells me the graph of the derivative function. You understand? The derivative just measures the slope. So I might be interested in asking this question. Now, what functions? I mean, it seems that if I understand anything about exponentials, if I forget for a moment that I don't know anything about them, if I take the derivative of a function, when will that give me the same function? You understand? And the question is, what can I say about a function I know nothing about? It's a riddle. And the derivative of that function is unchanged. So first of all, guys, let's play this game. How many such functions can exist? What do you think? This you can answer if you understand, if you have a concept of what the derivative is. How many such functions are possible whose derivative is equal to themselves? Exactly. There can be infinite, right? Aaron, you say one once I specify a value, right? If I just say the derivative of a function is the function itself, there could be infinitely many. Now, there could be infinitely many. Okay, the reason there could be infinitely many, simply look at it. If you found one function, then you can find another function, let's say a times f of x, and that's your gx, right? Now, if you take the derivative of gx, that would be the derivative of a fx. That will be a f prime x, which would be a fx, which will be gx. So if I can find one, I will find infinitely many, because I can just vary the constant. Okay, the constant can be any number, any c. It could be 1, 2, 3, 4, 5. I can multiply it by any number, and there will be infinitely many of them. Now, why would I suspect that there should be infinitely many of them? Because derivatives only speak about the slope, and the slope does not really refer to the position of the graph over the x-axis, right? So for this x, if I have a derivative equal to 5, that means that wherever the curve is located, it's locally a line segment with slope 5. But the line segment can be here or here or here or anywhere. You understand? There are many parallel line segments that have the same slope. To figure out the exact line, I need both slope and some intercept where it crosses the y-axis. Enough? Yes, enough. What would you like to? So this email you're supposed to send to, not to this chat, but to my email address with your first name, your last name, and telling me that you are from this section. Look at the syllabus that's located on my website. You understand, guys? So I have this this idea. Now I make the further stipulation. This I completely forgot that I'm talking about exponential functions. I just think, okay, what functions have derivative equal to, you know, to itself, and then what? And then I have this faint memory that the exponential at 0 is always equal to 1. So I think, okay, why not make my function equal, all right? When is that happening? It's okay enough, right? We'll wait afterwards. If you have more questions, I'll answer it after class. F of 0 is equal to 1. You understand why I just have this? I forgot everything, but there in my nightmares, I remember there was e to the 0 possibly equal to 1, or anything to the 0 equals 1. I might remember that the exponential inspired me to think about this problem. Now, guys, because you haven't really dug into more of this mathematics I mentioned last class, guys, you should think of it. Why is it so important? If you ever watched a horror movie, right? You watched about poltergeist, right? And the poltergeist, you come to this house and you see everything is turned upside down. Everything is broken. If you are a ghost hunter, you search for that one thing that the ghost did not touch. Maybe it's a 19th century painting, right? There is a strange, ominous woman in that painting. Why was that not crushed? You watched horror movies, guys, right? At least or watched a lot of movies, get some benefit from it. To understand the poltergeist, you want to understand the thing that remained intact, the thing that was not touched. It ends up being true in physics and mathematics, so you can solve amazingly interesting things if you understand what the derivative does not break, what does it not change. So the importance of what we're doing is to realize what the derivative is not changing. Are you clear? So we begin investigating what sort of function could that be. At 0, it's equal to 1. And notice, because I said 0 it's equal to 1, now every other curve that has the same derivative must be parallel. You agree? It must be parallel. It has the same, right? if there is, so you okay, anyhow, let me just forget about the parallel for a moment. So we investigated. So then we asked, could that be a quadratic polynomial? Could that function actually be a quadratic polynomial? And the answer is obviously it cannot, because quadratic polynomials are changed by derivatives. You agree? Take 3 derivatives to make it obvious, and the quadratic polynomial disappears to 0. But take no matter how many derivatives of that hypothetical function, it never disappears. You see that? So I find the difference. A polynomial of degree 2, any polynomial. I don't have to know what sort of formula you try, but I know that I will take enough derivatives. The polynomial disappears, but this function stays. Now, could it be cubic? It cannot be cubic. If you understand enough about derivatives, take 4 derivatives of a cubic, it vanishes to 0, but this function stays. And it cannot be any polynomial of finite degree, because if it's of degree n, take n plus 1 derivatives and it's gone. So if it's of degree 1,000,000, take 1,000,001 derivatives and it's gone. Do you see that? Because each time you have the power rule, the x to the million is the strongest thing, the longest thing that can stay. So it will drop its powers, shed the powers until it's gone when you take derivatives. You're with me? And then you have that leap of faith, which all of you should have watched Indiana Jones. Have you seen how he was going for the Holy Grail? Guys, you don't watch old movies. It's you lose connection with your past. So how many of you watched Indiana Jones, right? So there is this leap of faith that he makes where it seems that he will jump into precipice, but he makes that leap of faith, and that's why he's able to walk over that bridge. That leap of faith that we're making here to get to the Holy Grail. We should all go home and watch all of Indiana Jones. It will inspire your understanding of analysis. So that leap of faith is infinite polynomial. You see, if I cannot achieve it with a finite polynomial, let me try to do that with an infinite polynomial. Do you understand that, guys? It's just because I really love polynomials. I can calculate with polynomials, right? It's just multiplication and addition. I know what to do. So I make that hypothesis. I assume that it's just a polynomial that does not have a biggest power, whatever that means. And so my goal now is to figure out what are those coefficients. And how do I do that, guys? Well, this function I know nothing about. This mythical function is not changing under derivatives. And if I plug 0 into it, I get 1. So tell me, please, if you remember from last class, how do I get a sub 0? How do I get the first term here? What do I do? A sub 0, how do I get it, please? Type in the comments. F of 0, thank you, Aaron, and the rest of you guys. So in particular, what is a sub 0 equal to? The first coefficient is equal to, you can just say, what's the number it equals to? The first coefficient, what does it equal to? One. Are you seeing it, guys, why it's 1? It's so simple. Look at it, guys. Just feel this function. Look at it, plug 0. Everything is gone. Everything is annihilated except for the first coefficient. And I know this function at 0 is 1. So a0 has to be 1. Yes, I'm molding this polynomial. I'm shaping it like clay. At 0, it's 1. Now, could you help me figure out the next coefficient? How do I figure out a1? Remember, guys, you know nothing about this function, so there are very few things you do. It's like an escape room. What do? You can plug 0 and you can take derivatives because there is nothing more you know about this theoretical function. Yes, Ezra? Elazar, I'm sorry. Yes. Yes, guys? You take derivative. Now look what happens if I take derivative. Take the derivative of this expression, what do you get? Look at it. F prime of x, its derivative is not changing. But this polynomial, I take the derivative of each coefficient, I get a1 plus 2a2x. Right? This is a1, 2a2x, 3a3x squared, and so on. And then I can plug 0. Look at it. The only thing that stays without an x is a1 now. Plug in 0, you get 1. So a1 is also equal to 1. Clear? Now, if it's clear, tell me what's a sub 2. I know a sub 0 is 1. A sub 1 is 1. Now, what is a sub 2? Thank you, Jamal. Thank you, Sandra. And guys, you understand, not because you looked anywhere, it's just so obvious to you why it's 1/2. Correct, guys? It's not meant to be difficult. It's meant to be very, very natural. 1/2. Thank you, Celine, right? 1/2. Look how natural. Look at it, guys. Just a little bit, very, very little thought. And we are just able, it just flows out. Exactly, right? Both abstract implies calculation. So here, guys, I take second derivative. And in the second derivative, you see what happens. We get 2a2x. Right? And then I take the derivative of that. It's just 2a2. And everything else has an x. So when I plug in 0, this function is not changed by derivative. So it's just going to be 1 when I plug 0. But the polynomial, only the 2a2 is what survives. 2a2 is equal to 1, which means a2 is equal to 1/2. And similarly, if you take, if you want to get a3, you just take 3 derivatives. You get 3 times 2 times 1, or 3 factorial times a3 equals to 1. Yes? And so a3 is equal to 1 over 3 factorial, or 1 over 6. You understand how that works, guys? And I don't have to go with a0, a1, a2. I can say, oh, I now understand how to figure out a generic coefficient. So how do I figure out a generic coefficient? Well, let's see. So my function is f of x equal to all the way to some an x to the n and onwards, right? What happens if I take one derivative of this function? It's going to be whatever you have there, but here the n drops down. It's n an x to the n minus 1. What happens if I take another derivative? It's going to be the same thing, but now it's n minus 1 an x to the n minus 2. Yes? Are you with me? Do you see what I'm doing? I'm pulling x to the n towards the front, and I'm depleting the powers of x as I do so. Do you understand that what happens? The terms that have a smaller power, they will vanish beforehand, because once you have x to the 0, the next derivative will make that term 0. That's very obvious. Yes, guys? And that's not only just for this. This is something when you're taking Calc 2, it's called Taylor series, and that's very obvious what's happening there. So how many derivatives do I need to take, guys? Can you see n minus 1? How many more derivatives? How many derivatives do I need to take to get that term isolated, to get it to have no x, but not vanish? How many derivatives will I take? N. Do you all see that? What is the meaning of n? In other words, if I want to figure the coefficient a3, I will take 3 derivatives. If I want to figure the coefficient a sub 4, I will take 4 derivatives. Do you understand what we say when we say n, guys? If I want to figure a coefficient that corresponds to the millionth term, the a sub million, I will take 1 million derivatives. You understand what this n is about? It's just my way of saying all derivatives. All right, so that means that you can write it like this: f n of x will equal, look at what happens here, that's n minus 1. I would have had to reduce the powers until I get the last power of x, and now it's an, and now it's x to the power of 0, which means there is no x. X to the power 0 means very simply I'm erasing it, there is no x, you see? And everything afterwards has some x. Now what is this function? It's not changed by derivatives. This is still my function f of x. By hypothesis, it's this function that is not affected by derivatives. Yes? So I plug in 0. So I get 1 equal to f of 0, because this function is equal to 1 at 0. And what is that equal to? That equals to n factorial. This is just n factorial. Remember what is 5 factorial? It's 5 times 4 times 3. So this n times n minus 1 times n minus 2, all of it, it's called n factorial. So it's n factorial an. Everything else is 0. So what does it mean? It means that 1 over n factorial is my coefficient an. Do you understand what it means, guys? It means that this function is unique. There is once I say that at 0 it's equal to 1, because I have all those coefficients identified, that means that this infinite polynomial is unique. I mean, I now know what it looks like. I now made it in the flesh. So this is what we have arrived at. Do you see what this is a sigma notation for that infinite polynomial, just allows you to write it in a very compact form. It means plug in 0 factorial is 1, then plus plug in 1, plus plug in 2, plus plug in 3. So you see here is that thing written in expanded form. You can write it like this, but what it means is this in expanded form. You understand? Just this means n equal to 0. Put 0 instead of n, then write plus, n equal 1. Put 1 instead of n, then write plus, and you continue doing that. You see? So it's 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed, and so on and so forth. And here I just made I just showed you that if this is the definition of my infinite polynomial, under the derivative, it gives you f of x. Here I just told you that must be e to the x. Okay. I just kind of simplified it, but if you think about it deeper, e to the x by itself, it's a sort of meaningless expression. This function, some authors prefer to call it exp x, to try to get rid of this power on the top, you know, because again, remember what we don't understand what it means to raise a number by, even if you think you understand what it means to raise it by a fraction, you definitely don't understand what it means to raise it to the power of √2, for example, or to the power of pi. You're with me? So this e to the x is a sort of vague expression, but that polynomial expression is less vague because it involves operations I'm very familiar with. Good? So this is the way you call this function. Now, it's a completely optional thing, guys, okay? Completely optional thing. But if you're, of course, brave and you want to understand something deeper, I can show you that this function possesses all those properties I believed exponentials should have. It behaves like an exponential. Now, what does it mean to behave like an exponential, guys? You know that, for example, you expect 2 to the power of x times 2 to the power of y to equal 2 to the power of x plus y. Yes? In terms of a function, and that's for any real number. In terms of the function, you expect something like this. You expect f of x multiplied by f of y to equal to f of x plus y. So that's the same property expressed without putting anything on top, or, you know, right, without keeping that. So you can then verify many things about it, right? You can verify. That's the optional part. You just need to know the binomial theorem. I talk about it in my stat class. And here I used e to the x, e to the y, but really here is that verification. F of x times f of y equals to f of x plus y. I just multiply one polynomial by another, and I get that this property holds for all numbers, which means if I select an integer, it will be the same as f of 1 to the power of p. So when I select integer into the function, it does behave like the exponential I know, right? Like the number multiplied by itself. Okay, you understand what I'm saying, guys? So if this property is true, so then I can say that f of 3, it's the same as f of 2 plus 1, which means according to that property that it's f of 2 times f of 1. And then f of 2 I can break again into 1 plus 1. So it will be the same as f of 1 to the power of 3. So what is f of 1? F of 1 is what happens if you plug 1 instead of each x. Okay, so you will see that this behaves like an exponential function, but where it's very clear why you know, the original bookkeeping works for all numbers where it's clear, but it's also very easy to plug in non-integer values. So for example, what is e, for example? What is the number e? The number e that we were seeking can be obtained by plugging 1 instead of the x. See, it's because we basically understand that it behaves like an exponential. That's why we write it as e to the x. Plug in 1, you have 1 plus 1 plus 1/2 plus 1 over 3 factorial, you have this thing. Look at it, guys. And when I add this thing, I arrive at numbers of the form 2.71. And if I play with my calculator, still unfair, but if I play with my calculator, look what happens. This is very close to 1. Add more digits, you get 2.718. And you play with your calculator, and it's even closer to 1. So all the things that you were observing with the machine, they are confirmed. Okay. Are you with me, guys? I mean, I know I said something rather theoretical, but I hope you understand. I mean, I'm saying it's dangerous, of course, right? We're flying very high, right? You think e to the x, but not e to the x. I'm not sure what happens in your mind. How much of it are you able to save and process? But I hope a lot. 1 second. Hello, guys. I'm back. I'm sorry. So yes, Little Red Riding Hood. You just notice that's something you understand if you take probability. It's also because it's dangerous to be near me. Yes. He knows. Give me a second. So again, guys, so what we understand now is, you see, why do we can say e to the x? Because we actually, for the first time, witnessed an actual exponential. If you kind of follow this process, you can actually understand what it means to take all powers and understand why the exponential laws work. You understand, through calculus, through those derivatives, I'm actually able to justify all exponential laws with a little bit effort. That's why I said it's optional. You understand? You can forget about what I said and assume that e to the x is just equal to this thing if you are unable to think more abstractly, right? So I now understand. So basically, when I say e to the x, I'm also consider to say x to kind of not be confused with basically that's the first exponential that we have. And now, for example, if I want to know what is e to the pi, that's simply what? That's simply 1 plus pi plus 1/2 pi squared plus 1/6 pi cubed, and so on and so forth, right? You don't have to edit forever. You can just approximate. You just decide I stop after I edit 5 terms, or I stop after I edit 7 terms. And what your calculator can do is just add a lot of those terms, calculate it, and it gives you those values. I can understand every other exponential in terms of that function. So you understand, I mean, this function makes it mathematically clear what exponential laws are. Okay, I could have begun with this function, and I could have derived all the exponential properties. Good? So it's a very, very important function, guys. I hope you appreciate it. So we already spoke about one basic application in probability theory, am I right? We did that experiment with the liquid. You remember it? So if I decide after a hard class to drink 1 beaker of tea and 1 beaker of rum, by sipping from the tea, then pouring the rum and mixing it and then drinking it, the probability that my last drop is that of tea is going to be related to a very interesting limit. And that's the next, which is also a difficult part of that previous lecture. Here it is, guys. We concluded that when you do this calculation, you arrive at the limit of 1 minus 1/n to the power of n. And that limit, if you calculate it, it ends up being e to the power of -1, 1/e. Now, why is that 1/e? For that, you need to understand, and that's going to be very important, guys, this limit idea, okay? Super important, very, very, it works in compound interest, it works in decay, it works in basically on all the laws of probability or many other things. are related to that formula. So you see, I construct a recursive function. So this is where I play with the definition of the derivative. Limit as h goes to 0 of f of x plus h minus f of x over h is f of x, where f of x is going to be my e to the x here. Now I can avoid taking the limit by assuming h is very small. And I have this formula. I can rewrite that formula, which we did last class. I can write it as 1 plus h times f of x. And if you are very, very clever, you realize that you constructed a recursive procedure to compute e to the x. You understand what's recursive procedure? In other words, I mean, I already have the polynomial expansion, but here I can also do the following. I can say, what is e to the x at some point x? I only know what is e to the 0. So I will walk back towards 0. And this is telling me how I should walk back. So I should make very, very small steps. You see, guys, it's a function evaluated at a number, and that's approximately 1 plus a small step back times the position of the function evaluated at the position of 1 step back. So study this very, very well. It will give you interesting insights. For probability, I mean, it's a sort of complete must. I mean, you cannot go anywhere. Also, if you want to understand, of course, if you want to argue about how old is the Earth, right? So, for instance, I remember it's very interesting in the Old Testament, they say that, if I read it correctly, that the plants came before the sun and the stars. Okay, and so I read it, and I read it several times, and then it appears that the sun and stars, according to the Old Testament, appear later than the plants. And then there was, of course, people like Newton and many, many very, very intelligent people of the time. They, of course, were interested in all of it. They wanted to understand how old is the universe, how old is Earth. Now, when you have those estimates have to do with e to the x, naturally. Of course they would, right? So they have to do with exponential growth and decay. So, and such limits come around. So here we go, guys. And of course, if you read my lecture 0, the justification of the lockdown has to do with the exponential, right? So the fact that you were told to hide and not go to work and to not meet and not party has also, at least the justification. I'm not claiming the reason, because the reason is not there. The justification was made mathematical, right? And you can look at this. I analyzed it, you see, and I can show you. I didn't bother with lecture 0 as I did it in previous semester. But you can see the logistic equation. So the claim about people, no matter the initial claim that they did then, no matter what you do, the same number of people will get sick. Now, why did they make that claim? And if you think about it a little bit, they were using the logistic equation. They were using a sort of variant of e to the x. It's in terms of e to the x, slightly more complicated, but it's using e to the x as its constructing function. Okay, if you go back to lecture 0, you can see all about it, where I try to explain what's the mathematics of it. Okay, so yes, I hope, guys, that any of those things, or at least some of them, make you excited about it. So here we have the interval from 0 to x. I divided it into small steps. I made the steps visible, but really they're supposed to be microscopic. You understand? So what this formula tells me to do is this. It tells me that the function at x, the function at this point is the same as the function at this point multiplied by 1 plus x divided by the number of steps. Okay, and then to evaluate at this point, I move 1 step back and I multiply by an extra 1 plus x over n. So I walk all the way until I reach 0, and I see that the function is approximately 1 plus x over n to the power of n, and that becomes absolutely correct when you push n to infinity. I might give you other less illuminating but perhaps more rigorous description of the same thing, but I really like that. Makes it very obvious why that limit is e to the x. Okay, which means, guys, that 1 plus 5 over n to the power of n is what? What is this limit? Calculate this limit, please. It should take you less than a minute. It should be immediate. Type it. Exactly, Jeffrey. Exactly, Jamal. E to the 5. Thank you, guys. Now, what about B? What is B? E to the minus 3, Jasprit. Amazing. You all see that, guys? I mean, if you look at the definition, it's a difficult limit, I presume. I'm not sure how many of you understood my derivation, but that is what I'm trying to teach you guys. Not the particular formulas, not how to solve some stupid nobody cared about question. I'm trying to hopefully make you think through this material, so that influences the way you are actually looking at things. Good. So what about this? As n goes to infinity, 1 minus 1 over, and that's we already solved. That's e to the minus 1. And this is, you see what I do? I just place a plus here, and this number is minus 1 here on top of n. And this is root of 2. Very good. Okay, and this is just e to the power of root 2. So those limits are very important, guys. And let me try to, I'm not going to explain how this limit is important, guys. How many people do we have here? We have 34 people here in this class, right? Now, what does e to the x have to do with your birthday? Right, I do it in probability. Let's see what it has to do with your birthday, guys. So first of all, guys, what do you think? Is it very likely that 2 of you share a birthday, or not likely at all? So here, the people present in the class, do you think it's likely that there is at least 2 of you that have the same birthday? Or do you think it's not going to happen? So Jeffrey says unlikely, not likely. I'll tell you afterwards what happened in the morning, guys, right? Not likely, not likely. Just I want to see your impression, guys. So you see there are many days of birthday, right? And you have never met anybody that has a birthday that is on the same day as yours, I presume, right? At least I've seen many people, and it's very strange if I find somebody that has the same birthday as I do. Good. So let's test it, guys.
But you said same birthday, not like same year, right? If
yes, not
year,
the
then
same
that's
year.
a different situation.
Yes, I mean, you can always, I mean, you can say if it's the same second, the same, depends how you divide time, you can make it impossible, right? But same
day, it's possible, but if you say same date in year, and then
everybody
second,
understands possible, right? The question is, will it happen today? Let's check, right? I do not know if it will happen today or not, but let's check, guys. So we're going to do the following. Are you ready, guys? You will, I'm going to say January. I'm saying January right now, and you will tell me January which day, okay? So type in the comments if anyone is born in January. Okay, I suppose nobody was born in January. Now get ready to type. Now I'm saying February. How many of you born in February? 20, okay, January 20th. January 18th. And February 19th. Are we done with February and January, guys? Everybody typed it. So now March. Tomorrow, Sophia. Tomorrow, amazing. I'm not sure what should I do. Tomorrow is 12. That's right, 12. Yes, happy birthday. You just send me an address where you live, and I'll send you a math book, a very difficult one. Because that's what excites me. I mean, I don't understand anything else, right? So if people that get me like, my God, oh, they got me this thick math book, I get, my God, my favorite. That's what I dreamed about. All right. So anyhow, guys, so March 12th, and nobody born in March anymore. March 16th. Then after March, you have April, correct? April. How many of you are born in April? 24. Here we go. We found 2 unlikely people. 24 and 24. We already found some. You were surprised? Now let's see if we found more. I'll tell you what happened in the morning, guys. Maybe you can guess what happened in the morning. April, then May 24. Okay, thank you. Nobody else is born in May. Now May, then June. Who is born in June, guys? June 9th. Okay, and June 10th. And okay, done with June. Now get ready, August, people. In August, how many? I forgot July. That's right. Sorry, July. I am terrible at days and whatnot, right? So July 1 and July 25. My apologies, guys, right? And July 1, July 25. That's it, Sarah. And okay, August again, guys. If you type again. August 18th, 21st. Okay, September. Okay, 17. 21st. Only one person in September. Okay. October. 14 and 17. And October 1st. Okay. October 18th. Okay. November. '13 and 24. December. 13 and 13 and 24. Okay, well, we found one pair. Congratulations to the one pair, and congratulations to the person that has a birthday tomorrow, to Sarah, right? I'm terrible with names. Forgive me if I am. On December 29. Now, I expected this to be more likely to happen than not to happen, because we have 34 students here and people. In the morning, guys, somebody decided to have the same birthday as I do. It's the first time I met somebody that has my birthday. Right? So that was happening in the morning. When? September 16th. Good. So guys, was it likely or unlikely? So I'm not going to go through the calculations because I don't want to waste time. But here, guys, look what I do, guys. In the estimated calculations I get once I carry it out in probability, estimated likelihood that no people have a match is roughly 1 minus 1 over 365 to the power of if you have 40 students, it would be 40 times 39 divided by 2. That's my estimate. You see, look at it, guys. So you have formulas like this. You have this formula, then you have this formula. That's, I just calculated for you for 40. I can calculate it for any n. Within that formula, I can recognize that limit for e. You understand? So you look at it. It's 1 minus 1 over 365. Look at it. This is a large number. So you see, if I have this thing, I just want to have it to the power of 365, because again, I recognize that e is of the form 1 plus 1, you see, I recognize that if this is x, 1 plus x over n to the power of n, where n is huge, will approximately be e to the x. You understand? So I just look at this number. If it's a huge number on the bottom of x and as the power, it's going to be very, very close to e to the x. And because I recognize that, look what I do here, guys. So I have, for 40 people, if I have 40 people in class, then that would be 1 minus 1 over 365 to the power of 780, which I can write as 1 minus 1 over 365 to the power of 365, and here I divide it. You see, why do I do that? So that this becomes e to the minus 1. So it's e to the minus 1 to the power of 2137, which is about 0.12, which means that the probability that among 40 people I will find at least 2 matches is 88%. It's over 50% that I find matches if I have 23 people. Understand? I calculate it in general. So you begin to break even once you have 23 people in a room. The likelihood that they share a birthday is greater than 1/2. Good? And you might think, okay, this is just birthday, who cares? But the point is this limit appears again and again and again for very good reason. Right? The bigger, why you should not be surprised when you learn a bit more about it, you understand e to the x is special because it's a sort of unique function up to scalar multiple. That's its derivative is equal to itself. Okay, so that's very, very significant. It means that it plays a huge role. It's like the axle around which things rotate. If you studied Aristotle, the unmoved mover, right? It's that thing that is not moving, things move around it. It's that type of thing that you have. Okay, this is all you miss because you're not coming to probability. Most of you, I think. So we are now going into product and quotient rules, guys. So a few more derivatives. So guys, if I asked you to calculate the derivative of, just before I asked you to do this calculation, what would you have said? If I asked you to carry the calculation for 5e to the x, what would you have written? Derivative of 5e to the x, what would you say? Five e to the x, guys. Are you stumped so much? You think, okay, just how many fingers you have, like you're an LSD? Exactly. 5e to the x, it's not changed. You understand, guys? Derivative, so this is what we were learning, right? Derivative of e to the x is e to the x. So derivative of 5e to the x is 5e to the x. Since you didn't answer so quickly, let me check one more time. Tell me, what is this derivative, guys? So I have 3 minus 10x squared plus e to the x plus 5x cubed. Tell me what's the derivative and type very fast. All right. Thank you for those who typed, guys. You're still conscious? Are you okay, guys? Guys, you don't have a 1,000 mile stare, right? You were not like after a 5-hour interrogation without sleep, yes? Not yet. It's so easy for you. You feel fresh, you can resist. You're not ready to confess. You see, guys, why am I doing this? You ask me, right? What's the ultimate goal? I'm training you, right? To resist torture, interrogation. That's very difficult. All you have to do is just remember this class. Everything else would be easy. That's fine, Salim. Thank you. Don't worry about it, right? So I hope it's just easy, right? That's all it is. So it's minus 20x plus e to the x plus 15x squared. Good. I hope you all see that. Now, guys, what would you say? And you don't have to say anything. Maybe you don't like that question, right? If I asked you to take the derivative of x squared times e to the x, what would you say? X squared times e to the x, guys. Can you do that? Okay, 2x e to the x. That's fine, Jeffrey, right? I mean, right? If somebody points a gun and makes you answer, that's fine. But you can also resist, of course. You can say, well, I have to be very careful with it, to tread lightly or something. Yes. You think, Aaron, you live in America, I see. So, John, you think the derivative remains the same, right? So you think the function isn't changed. All right, guys. So let me teach you how to do it. Are you ready? Take a pen and write it very carefully. So here is what we do, guys. Look at it. Derivative of e to the x is e to the x. Derivative of x squared is 2x, correct? So then the derivative of x squared times e to the x is the derivative of x squared times the derivative of e to the x, which equals to 2x e to the x. Yes? Do you all understand? Confirm that you understood how I solved it, please. Right. Yes, I understand. I want to see 34 people writing yes. I see so far 7, 8, 9, 10, 11, 13, 14, 15, good. 16, good. 17, 18, 20. 20 people, that's how much? That's most of the class that's here, right? 21, 22, 22. That's it, 22, 23. Okay, somebody joins. Anybody else joins? Come on, come on. 24, yes, 25. Amazing. Anyone else? Anyone else? 25. So I have so far less than 10 people that haven't joined. That 27. Ooh. Let's say what we said. Yes, lol. I'm following. Yes, what do they say in the Bible? When the blind leads the blind, they all fall. Because if I decided that I'm not in good mood, I would feed you misinformation, because this is absolutely wrong. Of course it's wrong. Talmud? What do you mean Talmud, Elazar? I didn't read Talmud, but you mean when the plants came about, or what? That's interesting. So this, guys, is wrong. Thank you. Oh, here you go. Right. So we have an expert. I always wish to go back to. I always try to read a lot of the things. Try to review the Hebrew there, but I always stop at the time when they describe the Ark of the Covenant. When they bring it, they just have 4 pages of how it's designed. I feel like I'm building an IKEA closet. It's just too much. Right. So yes, it gets overwhelming. So it's wrong, guys. Now you see, guys, it's very easy to make mistakes if you if you're lost. If it's a new city, right? That's why everybody is just if you go to certain cities, they would right away recognize that you are a tourist, and they will pluck you clean. So you don't want to be a tourist in Mathland. It's very cruel there, right? They just right away pluck you clean. So how do you not be a tourist? You always verify everything. You always certify everything that you do. If you order a taxi, you certify that it's a certified taxi. And to us, it means that we prove. And so guys, let me torture you once more. Are you ready? Take a deep breath. It's a bit difficult. It's now going to be very conceptual. Are you ready? Here we go. We are going to derive the idea, we are going to find the derivative of a product of two functions. You see, the problem here is if I know the derivative of one function, well, we'll get there again. We'll get there, Elazar, right, later. So guys, we are first going to review what it means to differentiate a function in the geometric sense. Let's see if you can do that. So guys, the way you take the derivative of the function y equals to f of x geometrically is that you zoom in. Do you agree? You zoom in on that curve until it starts to look like a straight line. That straight line has to be the tangent curve. I hope you understood that. I spoke about it many times. I hope it's so clear to you that it cannot be anything else other than the tangent curve. For the very reason that if you zoom in, you make the x-axis very short, which means that all the possible points of x are very close around the point A. So that must be that when you zoom in, you are seeing the derivative tangent line. Do you understand what I mean, guys? You are zooming in at the point A. So A on the x-axis is your center, which means as you zoom in, the x-axis vanishes and you have that point. Let me again show you with an animation, just in case you don't like it. So still. Here, guys, right? So let me zoom in at the point 9. Here is the point 9 on the x-axis. Do you see that? I zoom in, I zoom in. You see? You can see the numbers I can see here. I don't see 1 anymore and I don't see past 14. Let me zoom in more. Now, do you see, guys, what numbers do I see? I see from 7.8 to 10.2, right? Now I can zoom in more. And what happens? Look at it. What's happening? Do you see that in this arrangement? Look at it. In this arrangement, I see all the way to 9.1. And the lower value, I think the way I zoomed in, if I put it perfectly in center, 9.125 and maybe 8.875. You understand? I see fewer and fewer points of the x-axis where the point 9 is in my center, which means that the second point, the floating point x f of x, is close to the point 4 f of 4, which means that I am observing that segment of a line. It looks like a line for that very reason. The function is differentiable. Are you with me, guys? Yes, you look how much like a line it looks. Now I'm going to use that idea. When I say what do we do when I calculate the derivative? You all watch movies, and some of the movies that you watch are terrible. Correct? Those are comics movies where you have I don't know, Spider-Man fighting against somebody else. So the actors playing Spider-Man and somebody else are prima donnas. They're not taking the action, right? They're difficult to deal with. But they have stunt doubles. The stunt doubles are cheaper and expendable. Right, so when there is a dangerous sequence, maybe fight sequence or some sort of acrobat sequence, the stunt double replaces the prima donna actor. Yes? Now, it's not very important, guys, but I used to think that kaskadyor must be a Russian word, and I was entirely wrong, because kaska is a helmet and dyorgat is to pull. I thought stunt double, it's such a nice word, sounds like helmet puller. But apparently it's French in origin and it's the same in many languages. So it's called kaskadyor, stunt double, just in case it helps you remember. Or in case you decide to learn Russian, which is one of my goals. So this is kaskadyor in Russian, kaskadyor is in French. Okay, guys, so what am I going to do with kaskadyor? So suppose that instead of wanting to calculate along the prima donna curve here, I need to know the value of the functions near the point A. So what I do, you see this red intervals. I will zoom in until the red interval is my full screen. You see this red interval. In that red interval, this red curve this is the tangent line curve, is essentially the same as the function curve. So the tangent line can carry the calculations instead of the function. It can be the stunt double. It can carry the stunts of the function. Are you with me? You understand what I mean? I'm going to use the tangent line equation to calculate the values for the function instead of using the prima donna function where calculations are difficult. Let me explain on a concrete example how that is supposedly done. Suppose, guys, that my goal is to approximate root of 9.01. Right? How do I approximate root of 9.01? Well, you all know that it's very close to 9. So the calculation is very close to 9. So what I will do is I will pick the root function, f of x equal to root of x. Here it is. And I will zoom in on that curve where x is 9. You understand why x9? Because I want to see what line does this curve look like near x equal 9? Because 9.01 is very close to 9. Are you with me? Here is that graph, guys. You see here is 9, and at 9 it's 3, and let's say if I want to calculate 9.01 or something like that, that's somewhere here. You see where the floating point, here is the actual 9, and here is somewhere here it is, right? That's what I want to calculate. I want to calculate it using this line, using the tangent line. So I will write a formula for the tangent line to carry out that calculation. So first, for the formula of the tangent line, I need to know the derivative of root of x. Now I can easily calculate it at any x. I take the limit, here I do it by definition, and I get that the derivative at x is always 1 over 2 root x, which means that the tangent line, when I zoom in near 9 root of 9, will be y minus 3, or y minus root 9, equal to 1 over 2 root 9 x minus 9. That's the equation. Are you clear, guys? That's called linear approximation, but I call it stunt double function or cascadeur. Linear approximation. So far, good? So you see, guys, here is how I use the stunt double. So instead of plugging 9.01 into a root, I plug 9.01 into the linear equation, into this formula. You see, instead of plugging, this is f of x, right? In this region, there is basically no difference between the actual code. The elevation of the curve is the root value, right? So at 9, it's 3, right? And then if I plug 9.01 in here, this calculation is very easy to carry. I just use addition and multiplication. A very easy calculation here, right? I'm not guessing anything, so to speak. You understand? If you understand, guys, you will help me now figure out an approximation to the following. Okay, that's your now task to see if you understand it. So I have, I want you to estimate root, the cube root of 8.9. Estimate the cube root of 8.9. Do it the best way you can, guys. Not with a calculator, of course, right? That's not the point. What? Give me the formula that you used to estimate, Brianna. You understand? We are not learning how to approximate root of cube root of 8.99. That's not interesting to us, or 8.9. We are trying to understand the idea of the geometry here, of the stunt double. Yeah, but guys, see what I'm saying is stand double. Give me the stand double if you understood it. You see, it's not a numerical analysis class. I'm not interested in this approximation really. I'm more interested in if you understand the stand double idea. Okay, I will wait one more minute and then we'll do it together. Your 1/4 is, I think, wrong there. I think it's not 1/4, it's something similar. Jasprit, but almost good. All right, guys, here is what I wanted from you. You see, what function are we dealing with, right? So what is my function that I am using to calculate? What's my prima donna function? My expensive actor function. Can you tell me, please? F of x is what? No, f of x is not a constant. What's f of x? The cube root of x. Thank you, John. Precisely, right? So it's the cube root of x. I'm just taking cube roots. You agree, guys? Of whatever number. So I can write this cube root as x to the 1/3. Okay. Now, what is the derivative of this function? We can do it in so many ways. We can do it by geometry. We can do it, you know, if you understand it. But let's right now imagine that everything is fine and the power rule works for fractions as well. Remember, we proved power rule only when for x squared cubed to the power of 3, only when it's an integer. But the power rule ends up working for every number that we can verify. This is 1/3 x to the power of 1/3 minus 1, which is minus 2/3. Good. Now, what point are you going to zoom in at, guys? What point do you decide to zoom in at? I should have selected not 8.9. My apologies for this. I wanted to say, because the cube root, I wanted to say 7.9, right? It's nicer to zoom in at 3, but hopefully you forgive my mistake. You zoom in at the point 8. Yes, at the point 8. Because why did I select that point, guys? It's because I see that cube root of 8 is very simple. Cube root of 8 is 2. So I zoom in at the point where the x coordinate is 8 and the y coordinate is 2. Zoom in. Right? Now, what will I see when I zoom in, guys? I will see the tangent line. What's the equation of the tangent line? The equation of the tangent line is y minus 2 equal to the derivative at 8, x minus 8. You agree? Now, what is that derivative? Derivative at 8. So f prime of 8. That's 1/3 multiplied by the cube root of 8 is 2 to the power of 2 is 4, so it's 1/4 because there's a minus, right? So it's 1/3 times 1/4. So the answer is that this is y minus 2 equal to 1/12 x minus 8. You're with me? So I got the tangent line. Now you understand what's the point of it, guys. What's my point? My point is that if x is very close to 3, x is very close to 3, sorry, x is very close to 8, then the equation y of x equal to 2 plus 1/12 x minus 8 is a very good way to calculate the value. It's very similar to the actual value. So for instance, y of 7.9 will be 2 plus 1/12 7.9 minus 8. And this is easy to calculate. And that will be an approximation to the cube root of 7.9. You understand what this is where I used the Stunt double. I used a less difficult function to calculate the value for the more difficult one. Clear? That's what the Stunt double is. And when you zoom in on a curve, you're seeing the derivative tangent line. In other words, the Stunt double, as I call it. It's called linear approximation, what we just did here. Do you understand it, guys? It's very simple. Just the tangent line can be used to calculate in place of the original function. Another one. 1/4 came from, let's see. 1/4 came from plugging 8. Look at it. 8 to the power of minus 2/3. It's the same as 8 to the power of 2/3. Now that's the same as 8 to the power of 1/3 squared. That's just algebra, guys. Look at it from this equation. So you have 1/3, 8 to the power of minus 2/3. What is that? That's 1/3. The same thing as 8 to the power of 1/3, then squared, then to the power of minus 1. Yes. Now what is that? That's 2 squared. That's 4, and 4 to the minus 1 is 1/4. Clear? So it's just basic arithmetic that we did here. No, I hope you understand, guys. Okay, one more. I want you, I mean, you can actually do it in so many ways, but suppose that we have this function, guys. I want you to tell me approximately what is e to the power of 0.01. Use that procedure. Elazar, but e to the power 0.99, is it any different from 0.01 as the power of e? What is the only easy power of e, and what is 0.01 close to? Exactly, Jeffrey. That's right, Aaron. So y is equal to 1 plus x. All right, so let's do it together, guys. First of all, why did you stop? Don't you recognize this thing? This is, first of all, 1 plus 0.01 plus 1/2 0.01 squared, and you can just decide where to truncate, right? This is for e to the x, we actually already computed much better. We have a much better approximation than linear. And if you have to take the linear approximation, it's right over here. Yes? Now let's try to do it just as if we pretend that we don't know that. So our function is f of x equal to e to the x. What's the derivative? The derivative is e to the x. Yes? Where do we zoom in? At what point do we zoom in? Now 0.01 is close to the point, to the x coordinate 0, 1. So that's where we zoom in. And because this point 0.01 is very close to the point 0 on the x coordinate. Yes? So we zoom in there, and what do we see? We see that the equation of the line is going to be y minus 1 equal to the derivative of the function at 0 multiplied by x minus 0. Now what's the derivative of the function at 0? So that's y minus 1 equal to f of 0. Derivative of e to the x is e to the x. So what is that? This is y minus 1 equal, f of 0 is 1, and this is x. So we have that y equals to 1 plus x, which, by the way, if you look at e to the x, it's 1 plus x plus 1/2 x squared and so on, right? We can make a very sophisticated Stunt double, but the linear Stunt double is here. It was immediately available to us. Yes? All right, guys. So then how are we using this idea? Good, Moshe. How are we using that idea? We can use it to figure out the derivative. Now, why can we use that, guys? Let me try to use geometry to figure out the derivative of f times g. Stunt doubles are supposed to do everything instead of the function, right? So abstractly, if I want to differentiate a function f of x at the point A and g of x at the point A, well, not even differentiate. If I want to understand what the function is doing to x, where x is very close to A, then it's doing essentially the same as the tangent line is doing. This is the equation of the tangent line. Are you with me, guys? F of x is essentially f of a plus f prime a times x minus a. If x is very close to a, this equation of the tangent line is a very good approximation. Everybody is clear where I get this equation, guys? This is just doing that process abstractly at some point a. If I zoom in on the graph y equals f of x near a f of a, what equation will I see? I will see y minus f of a equal to the derivative f prime a x minus a, which means I will see that y of x is equal to f of a plus f prime a x minus a. Are you clear? So this is just doing it abstractly, which is what it is really for, guys. It's not what you see, it's not to carry calculations. This procedure is essentially very useless for calculations. It's not the way I would calculate roots, because look at it. Root of what is root of 5? How is it? Root 5 is not close to any nice number, and then you have to worry about how close and whatnot, right? So this procedure that is linear approximation is useful conceptually, because it gives you a way to go from one formula to another. So guys, let's see if you can help me with this last calculation, just a little bit more, and we're done. So if f of x is this, which, by the way, x minus a I will write as dx. Dx is supposed to be very small. Like in here, you can see dx, let's say if I zoom in near 9, dx is this wing essentially. It's how far away can I be away from 9. So f of x is essentially this guy, and g of x is essentially this guy. Now, if I am supposed in my movie to multiply f by g, what do I do to the stunt doubles, please? Right? If the character f is supposed to be multiplied by character g, what happens to the stunt doubles? Guys, I think you haven't been watching movies lately, right? I guess the movie theaters have been closed for more than a year. You forgot what movies are like. Hmm? Well, it's good. You should watch better movies. My question is, if in my scenario, I'm to multiply, remember, I want to find the derivative of f of x times g of x, which means I want to see what happens if I zoom on the curve f of x, g of x. What line will I see? Right, so but the way I can figure out the calculation is that if I have to multiply f by g, they are hard to calculate. F times g is hard to calculate, but the stunt doubles are maybe not as hard to calculate. Right? If there is a sequence of function between f and g, I can simulate that sequence of function by their stunt doubles. Don't you understand why I call them stunt doubles? So it is, I need to multiply by if I multiply f times g, I multiply the tangent line by this formula by that formula. Look at it. F of x is essentially doing this. G of x is essentially doing this. In other words, this is the way the x is processed. You understand? So if I multiply two numbers, and this is approximately what those two numbers are, I just multiply the approximates. Are you with me? I think you are fried, huh? You are fried. I'm not getting anything, and we have 5 minutes left. You see, guys, we need to be imaginative. That's the thing. You see, it's actually almost like a small step in your imaginative. So let's do this, I suppose, right? So who are parallel? I mean, the lines. No, I didn't say anything about what's parallel to what. G, the derivative for g to the derivative of f. Why? No, I have no idea. All right, guys. So since you are so tired, this is what we are going to do. I showed it to my students in probability, and I think it's a good thing. I think you know exactly what the answer to that question is. Okay, there is a very interesting museum. Let me just tell you, so I don't have to even translate it. In some town in Germany, there is a very interesting museum. In that museum, the exhibits come from all over the world, and the exhibits always appear in pairs. You with me? Always in pairs. And the workers of the museum have to be very careful not to mix the left exhibit with the right exhibit. What is this museum showcasing? That's the question. And I guarantee, guys, that all of you know the answer to it once you hear it. Mirror images, but then what does it matter if you put them across? You understand, guys? I can show you how the knowers played it. It took them many attempts. They failed. My brother knew the answer to it, and one person from the morning class knew the answer to it. Let's say if you guess it. You understand? In each exhibit consists of two objects, and the workers of the museum are very careful not to mix one with the other. What are those two objects? What is this museum of? Okay, right, but those are not those are difficult to mix, right? Left hand and right hand are not the same, guys. Think about it, guys. And the way you play, you throw every idea, even if it's ridiculous. Maybe somebody else knows it or figures out because of it. You can do it. Come on, ideas, guys. What could it be? Something that is easily mixed up. What's which is which? It's very simple, right? I can show you. I can say what somebody said. Okay, Jeffrey, fake and real artifacts. Well, that's very interesting what you say. So Jeffrey, I would say Jeffrey came with a very good solution. Essentially, that is exactly it. You know what this museum is of, guys? Plagiarism. That's why you should all know it very well. Last semester, half of the class were added to that museum in Germany. You understand? Don't do that or I will stuff you. Soon there will be an exam. And with that, sleep well. Good night. Have a great weekend. Or yes, I'm not gonna. I mean, if you have quick questions, we can do it. Today I kind of. Which town in Germany? Have you been to Germany, Elazar? I don't remember which town. I can check if you want to. But you speak German, Elazar?